would be, minus 2a2 would be a1 plus a naught minus 2a2 minus 2a1 all divided by 6. Something cancels here, right? What did I do? I wrote it again. Yeah, sorry. Okay. A naught minus a1 over 6, all right. And you can see you can solve this for a4, but I'm gonna stop here. Well, fine, I'll do it. A4 is what? No, I'm not going to do it. I refuse. So, I mean, I have enough to illustrate the method. So what we've got is y is equal to a naught plus a1x plus a2x squared plus a3x cubed plus dot dot dot, right? But what that actually is we're going to use a naught and a1 as our parameters, right? So there's your a naught, there's your a1. Don't do anything with those. A2. Well, a2 was parentheses a naught plus a1. Well, excuse me, minus a naught plus a1 over 2 times x squared, right? And then a3 was 1/6 of a naught minus a1 x cubed, right? And so you see then the solution we get here is we have a naught times some stuff, right? So you can start to see the two fundamental solutions appearing. The one of the fundamental solutions has power series expansion 1 minus 1/2 x squared plus 1/6 x cubed plus dot dot dot, and then you've got plus a1 times x minus 1/2 x squared minus 1/6 x cubed plus dot 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 dot. And so we can recognize from the viewpoint of our general discussion of the theory from before that these are the fundamental solutions. This is the y1, so to speak, and this is the y2. And a naught and a1 are playing the role that c1 and c2 played before. Do you guys see it? So if I was so unfortunate as to face a forcing term, right, if I was to put some inhomogeneous term on the other side, like here, f, if I was to put something there, I know what to do. I use variation parameters subject to these homogeneous solutions, and I could do power series calculations to keep as many terms as I wanted to. It may or may not be possible to recognize the fundamental solutions as elementary functions. They don't have to be elementary functions. I think generically speaking, the problems which are nicest are ones where your y1 and y2 are like even and odd. You know, there's this. See, this is so nice. You get a recurrence relation, right? But it kind of links even and odd powers or something. Something like this problem is so much nastier because you see every recurrence, what you identify as be the recurrence relations, they're linking not just two coefficients, but 3 different levels of the coefficients. So it just makes sorting out this kind of recurrence a lot more nasty. But it can be done. It's just a question of perseverance. So do you see the method? That's I mean, in terms of raw calculation, that's, well, okay, there's another trick thing that you can do. Like, if you're given initial conditions, you can build them in, right? Like another Taylor's theorem sometimes used. So if you know that y of 0 is, say, y naught, and y prime of 0 is y1, then of course the solution you should guess would be y is equal to y naught plus y1x plus c2x squared plus c3x cubed plus dot dot dot, where these will be given constants, and that actually, that even for an ugly problem like this can still work out nicely. You'll see that in the homework. So, okay, so natural question to ask. So, okay, there's this thing you can do. You can substitute a power series expansion in, right? Where do these series converge? Like, what's the theory of convergence for these solutions, right? There's a very, very simple and relatively, yeah, sure.
What would it, I know it converges
Well, where they converge, I mean, if they don't converge, they're not solutions.
Okay.
So these are the, I mean, if I tell you I have a function defined by power series, then that's only a reasonable statement in as much as that power series converges. I mean, you know, if I tell you the function's defined by, you know, x to the n over n, summed from 1 to infinity, well, when you hit x equals to 1, you got 1 over n, which is the harmonic series, and then you know 1's not in the domain. So that's the next question to ask is, like, given the differential equation star, right, where p and q are functions, what's the theory of convergence? Well, let me just tell you what it is. It's really actually very simple. I mean, I don't know how simple it is to prove this. I don't know if I have proved this. I'm not sure if I have or not. Maybe Bailu and I did. I don't know. I can't remember. I'm not sure if this is a theorem we proved in the context of the A algebras yet or not, Bailu. What I'm about to state, it's hard for you to know until I write it. So suppose P and Q are not just functions. Suppose that they're analytic functions of x. What's that mean? So that's some interval. So to say that they're analytic, we're talking about real analytic. What that means is that those functions p and q can be expressed as power series expansions in x, and those series converge at all points in the interval I. Right. Well, if that's the case, then the solutions y1 and y2 likewise converge on i's. Likewise converge on I. Although I think I have to put some parenthetical comment here, ignoring endpoints. Right? I mean, what are possible domains of convergence for real power series? You remember? I mean, this I is not just any old interval. It has to have very specific form. It has to be like one of these guys, right? Because we're centering around 0 at the moment. I guess that's I mean, sorry. If I had some other, I mean, there has to be some center to the interval. So I guess if the center was x naught, this would be r plus x naught and x naught minus r, right? But it could be that the endpoints are included one way or the other, or both included. And then, of course, the other possibility, negative infinity to infinity here. Yeah. Half rays, like the other kind of intervals, the rays to infinity are not included here. Now, if we've had complex analysis, you recognize that these, of course, as just being the intersection of the disks of convergence for holomorphic functions as they intersect the real line. You got those cases, and there's connection there. But that's it. I mean, so if the functions are analytic, there you go. Right? So that's very comforting. So I knew a solution existed for that problem we just worked out before I did work it out, because the one I just erased, what were our coefficients were e to the x. E to the x is an entire function. Its power series converges the whole real line. Yeah. So I know that. Okay, so then the next question to ask is, okay, so those are called, if that's the case, if p and q are analytic on some interval about x naught, so if p and q are analytic at x naught, what that means, of course, is that there's some interval containing x naught on which p and q can be represented by power series expansions which converge. Then the solution exists, at least on that interval, and the solution is also analytic. Okay. But that makes, then the next knot is called an ordinary point. Okay? So how to solve differential equations at ordinary points? Very simple. Just plug in the power series, work out the recurrence relations. It's pain, but you can do it. Then the next question you would ask is there more? What if you're not at an ordinary point? Can we say anything in that case? Right? Let me show you an example of a case. We already covered an example of a differential equation which didn't have an ordinary point. Let me show you which one it was. Do you guys remember? It was so long ago. I mean, it's been like hours at least since we talked about this. Maybe 2. How about this? Excuse me. X squared y prime prime, come on, plus xy prime plus y equals to 0 as an example. Now that's not in the right format yet, right? To make it in the star format, what do I got to do? Divide by x squared, right? So this is y prime prime plus 1 over x y prime plus 1 over x squared y. So identify that p is equal to 1 over x and q is equal to 1 over x squared. Certainly, p and q are not analytic at x equals to 0, right? However, if you studied complex analysis, you'll recognize them as being relatively benign failures of analyticity. I mean, they're almost analytic in some sense. They're Laurent polynomials of low order. I mean, this is a pole of order 1, a pole of order 2. So here's another definition. If the limit as x goes to x naught of x minus x naught times p of x exists, and the limit as x goes to x naught. And you guys should check me on this. I'm about 90% sure what I'm writing is right, but if you find different things in the book as you're studying, do let me know. I'll make an add note to this video. X minus x naught squared times q of x. If these both exist, then x naught is a so-called regular singular point. So for the Cauchy Euler problem, at least in the n equals 2 case that we're thinking about right now, what can we say? So I divided by x squared to make it look like our current fair. So you have limit as x goes to 0 of x times a over x, which is a, and the limit as x goes to 0 of x squared times b over x. So this limit stuff, guys, if you haven't had complex variables, it's basically, the reason we're making this up is because you don't know what a Laurent series is. If you knew what a Laurent series is, you could kind of see through this without this limit stuff. You could just kind of recognize, oh, okay, well, it has a Laurent expansion, but the pole is only order 1, the pole is only order 2. If they had a pole of order 3 for q, or if you had a pole of order 2 for p, you'd be in trouble, because then these limits wouldn't exist, conversely. But these limits do exist, and so that means that x equals to 0 is a regular singular point of the Cauchy Euler problem. I don't really have much to say about irregular singular points. There is a theory for certain problems with irregular singular points which is known. If you want to read more on that, you should look at a book like Coddington and Levinson, the classic, but that's really more of a graduate level book. those problems are a little bit beyond our pay grade. This is even getting on the edge of it. Not yet though. There's a method that's known to solve differential equations with regular singular points, but I don't want to write it out. I'm going to use the projector here if you don't mind. I mean, we already know that they can be solved by relatively elementary fashion for the Cauchy Euler problem. The question is what else is out there, right? This brings us to what's known as the method of Frobenius. Or Frobenius method. And I will say, well, I won't say anything yet. All right. I will withhold my... Belu, is the sound still making... It's still bouncing? Okay. Do check on that. By the way, I have given you guys a quick... Oh, I should turn off the lights. Otherwise... I think it'll pick it up if I do that, won't it? I think it'll still pick it up with that. You think I should turn them all off? All right. I might fall asleep though. Ooh, very relaxing. All right, so excuse me. I just made a list of all the most popular power series expansions, ones you ought to know, and my standard bag of tricks from Calc 2. All right, anyway. So here's a couple of ordinary solution problems. We've worked through one carefully. This is a really good example. If you don't do anything else, do this example. Problem example 4.2.2. This is a really nice, slightly tweaked version of the one we actually did with sine and cosine. But let's see here. Yep. So I have a few examples. Yep. All right. So as we defined ordinary point, singular point is a place where one or more of the coefficient functions p and q are not analytic. But if x minus x naught times p of x and x minus x naught squared q of x are analytic at x naught, with the understanding that you clear out the factors. I mean, this is made rigorous in terms of the limits I wrote down. But another way you could say that would be that x minus x naught times p of x is analytic, and x minus x naught squared times q of x is analytic. That would make it a regular singular point. Okay, so here it is. A solution of y prime prime plus py prime plus qy equal to 0 centered at the ordinary point x naught can be... Oh, okay, so this theorem is actually a couple different things. So what I'm doing in this theorem is collecting together my thoughts on all the way domains work, okay? So for ordinary points, if you're at an ordinary point, the way it works is the solution, the domain of convergence is as big as it can possibly be until it bumps up against the next singularity in the complex plane. So, for example, if I'm centering my solution at 2, right, and there's something like at, say, minus 1 plus I. So maybe I've got something like y prime prime plus 1 over x plus 1 quantity squared plus 1 y prime plus y equals to 0. Something like that could be my differential equation. You can be able to get that? So suppose you have this differential equation, right? The thing is, when x is equal to minus 1 plus I, this is 0. So that makes minus 1 plus I a singularity of this differential equation. So if I was finding a solution of the form like this, if I was finding a power series solution centered at 2, all right, then I know what the radius of convergence is going to be for that. All I have to do is just like that. This, whatever. Let's see here. I can't. What have I done? I guess it doesn't That can't be right. Oh, well, I guess it's not the full circle though, is it? It has to be symmetric here, doesn't it? All of a sudden, something seems wrong to me. I think it's just me. So this distance is what? 0 to 10? Yeah. So this will converge on 2 minus the square root of 10 to 2 plus the square root of 10, and possibly the endpoints. Or possibly not. I don't know. All right. So that's, I usually ask a question about that on the final. Find the interval of convergence. Basically, the whole question is, there is a singular point, and how far is it from the center? Visualize it in the complex plane, then you can figure out what's the biggest interval of convergence that you can get there. It's a standard question. It's not hard once you get it. Go ahead. Got it? I'm used to people having camera noises. It's confusing when there's no camera noises, just silence. All right. Now, for a regular singular point, though, that gives us a different kind of domain. There we get those open rays, like the domain of convergence will be like from the singular point to infinity, or from the singular point to minus infinity. Singular point itself, of course, not included. So it's weird. The domain of convergence for the Frobenius solutions, it's defined in some sense by its edge, and it's always infinite. But as far as I know, I'll show you here. So here's the Frobenius method. So we assume that we've got a singular differential equation at x equal to 0, but x times p and x squared times q are analytic at x equal to 0. So I'm assuming it's a regular singular point, okay? So what you do is this. You suppose there exists a number r such that a sub n times x to the n plus r from n equals 0 to infinity provides you a solution to the differential equation. Now, at first glance, that doesn't seem all that different. But there's something you should know about the number r. It doesn't have to be an integer. It could be a fraction. You see, these are not power series. These are something entirely different, which is why they're not subject to the usual rules and conditions, terms and conditions, if you will, for the structure of the convergence sets. They don't have to converge on just open intervals or half open intervals or all of the reals. Other things are possible. So you plug it in. And of course, there's a significant amount of analysis missing here. I have not shown you the theory of convergence for such non-power series, right? There's all kinds of analysis missing here, but plug it in. Assume that you can differentiate term by term. You can. And when you do that, and you start grouping terms, you can do so order by order. The lowest term possible is called the Indicial Equation. The Indicial Equation we've already seen. It was the characteristic equation. It was exactly the characteristic equation we saw back in the Cauchy Euler problem. So when you do this order by order, what pops out at the lowest order again is this thing. Those are the constant terms from plugging it into the differential equation. But look at what that is. That's r times r minus 1 plus r times p naught plus q. So basically what's happening with the Cauchy Euler problem is it's a Frobenius series where only the initial terms exist, and then everything past those is 0. So for the Frobenius solution, the Cauchy Euler problem is to the Frobenius problem kind of like in the same way ordinary polynomials are to Taylor series. It's like, find the Taylor series for 1 plus x cubed centered at 0. And then, but people will leave that blank. It's like, oh, there's a great satisfaction handing that back and letting them see it, and then they're going, oh, no. Although some people still don't understand. I don't know. Anyway, as you can see, that is exactly the thing we saw before for Cauchy Euler. That's no accident because Cauchy Euler is the most basic case of this. And then you've got other stuff, and then there's the next one up. But how do you solve these? The same way we solve the other ones, just bit by bit, power by power, bootstrap your way up. That's how you get the first solution. All right? Now, of course, I guess, man, I don't want to do it, but I suppose you could use the boxed equation for the second linearly independent solution to find the second solution from the first if you wanted to. Ugh. We might do that, I don't know. Anyway, honestly, one of these takes me forever to work out correctly. And there's sneaky ways that the coefficients can get intertwangled. But here's an example solution. Looks something like this. You see you got like 2/3 powers and then these power series of fractional. And then over here you just have a plain old honest to goodness Taylor series solution. So here's the weird stuff, and that's kind of what we've seen before. This one, I think this one's kind of an accident that you found a general solution this time. That doesn't happen. Let's see here if I have another one. Anyway, so I don't want to bore you with these. Of course, you can have a complex case, right? If your indicial root is complex, then you've got to like solve the corresponding complex problems. You get cosines and sines of logs as it happens, because the way to understand, oh goodness gracious, how to say that? The reason that's happening, why are there logs? What was my, goodness, I like plus 2i, right? So I was trying to, you're writing down, you found a complex solution, something like x to the n plus 2i, right? So that is really x to the n times x to the 2i. And then this you can look at as what? Right. Which is x to the n e to the 2i ln of x. But then by Cauchy Euler's formula, that's x to the n cosine of 2 ln x plus I x to the n sine of 2 ln x. So that's where the logs are coming from, and the sines and cosines. It's Euler's formula. It's always Euler's formula. And the issues of multiplicity of the I mean, in complex variables, we worry about the multiplicity. There can be more than one value it takes, but that somehow goes away because we're looking for real functions. So that ambiguity gets washed out here somehow or another. Anyway, I'm getting a little bit beyond the border of who I usually talk about. Anyway, what I'm trying to get at, if you find a good book on this, for example, Boyce and DePrima, I think, or Rabenstein, Nagelsaf to some degree, there are a bunch of different cases. If your indicial solution has two roots, and the two solutions to the indicial equation, if they don't differ by an integer, it's pretty simple. If like the difference between R1 and R2 to the indicial equation is like 3/2 or something, then you just do the Frobenius method. You plug it in, you solve the recurrence relations, you get two Frobenius solutions just like that. If they differ by an integer, if the difference between them is an integer, then something else happens. And then it depends on which one's larger. I don't know. There's like 4 different cases. It's somewhat complicated. My notes don't cover all of it. I mean, my notes are slightly incomplete on the Frobenius method at the moment. So I want you guys to be aware of it. Many of the classical problems in mathematical physics, Airy's equations, other things, are regular singular points. So this is actually the technique we use to find the series expansions for many interesting special functions in mathematical physics. So definitely a second course in differential equations would do a lot more with Frobenius. I show you enough here for you to make sense of it, I think. but my treatment is not complete. I will admit that. Huh. This right here is an unfinished thought. I mean, there's some, anyway, you read this, you let me know what you think about it, okay? Section 4.4.1. All right, let's see here if I have anything more to tell you. That brings us to systems. So with that, I'm going to take a short break here. We can stop the video for a second. Break for 5-10 minutes if you guys don't mind.